So today we are going to geek out like Destin on Smarter Every Day. We're going to do it about one thing to do with the violin. See, I started my life out as a mechanical engineer, and we could do a whole ton of calculations about what this is, but we're going to use really rough numbers and just consider the forces that are trying to break this violin in half, and then try to consider what the forces are like for a cello or a stand-up bass. Those forces are immense. So if you look at this structure, as I mentioned in another video, this thing looks like a suspension bridge, right? This could be the tower. These are the cables that hold the deck of the bridge up, and this would be the driving surface we would drive on. Well, that's how a violin is structured. And the forces to hold it together are what we're going to calculate right now. See, Eric, the luthier, keeps saying that the force on these feet at the base of this bridge, this our suspension bridge tower, this thing's called a bridge, the forces on those feet are approximately 100 pounds per square inch. Well, if you put that foot and that foot together, it might make up a quarter of a square inch. So 100 pounds, quarter of a square inch, 100 pounds per square inch, quarter of a square inch, that's 1/4. So it's about 25 pounds. Well, if you know that as a really rough number, you can calculate the force of the strings that are trying to crush this violin. And we're going to do that right now. It goes like this. The tension in a cable or anything, a string, that is being displaced to the side, like those are by the bridge, you can represent it with a little drawing like this. I'll just draw it like this. We're going to assume it's just connected at 2 points, and we're going to assume it's symmetrical, because that makes the calculation so much simpler. Well, that distance that it's displaced from this line is called d, little d, and the length from there to there is called big L, like that. And the force pulling on it at each end is called T, like that. You have a T at each end. And the formula to calculate the forces is FL over 4D. So we've defined everything except this F, and F is the tension that it takes to displace it this way, this far, D. So this is the force F. Okay? And we've said that that F is, we can approximate it by referring to the pressure on the feet of the bridge, and that's about 25 pounds. So let's work that out. If F is 25 pounds, then T, which is equal to F times L divided by 4 times D, F is 25. L, well, if you measure a violin string, they're about a foot long, 12 inches. So you got 25 times 12 divided by 4 times D, and the displacement, how far is a violin string displaced from straight? Well, in this case, since we're working in inches, we can just say about a ½ inch. It's a ½ inch off of straight. So we put on the bottom 4 times a half, which is 2. And then you do the calculation. You say 25 times 12 is, how much is 25 times 12? 300 divided by 2 is 150 pounds. 150 pounds. That's what that calculation works out to. So, and that is the tension T. Well, that is how tight the strings are. How much force is being put. If you stood this violin on a base and put 150 pounds on the end of it like this, that's the equivalent of the force of the tension of those strings. You know the old saying, tight as a fiddle string? That saying exists because fiddle strings are tight. So there's 150 pounds trying to bust this thing right in half. It's amazing it survives the night. That's all I can tell you today.